Okay, you can ask me about that at lunchtime. So what we've learned a little bit in this course so far is that we can do a very good job of predicting the thickness of sea ice once we know its thermal properties. But we saw that sea ice is a mushy layer. It's a mixture of solid ice crystals and interstitial brine. And that solid fraction of brine, phi, affects the thermal properties in typical climate models. That's used as a parameter, and it causes one or two problems. If we really want to predict the volume fraction of ice in sea ice, then we need to understand brine transport. And in addition, the brine that escapes from sea ice into the ocean is one of the contributors to the density of the ocean and to ocean circulation. And so this lecture is going to be really all about the dominant mechanism, which is brine drainage, by which brine gets out of sea ice into the ocean. And what we're going to see is that we're going to have to understand things on really very small length scales, on length scales of a few millimeters. On the other hand, if I'm talking about a climate model, we are having to use a resolution that will typically resolve an atmosphere of about 10 kilometers thickness, an ocean of a kilometer thickness. And as far as those models are concerned, sea ice is this rather thin, 1 meter thick interface between the ocean and the atmosphere. And we also have to bear in mind that the horizontal resolution of typical climate models is about 30 kilometers. So somehow we have to parameterize all these small-scale processes in a way that can be used conveniently in this context. So let's start by looking at some sea ice. This is artificial sea ice grown in the laboratory. You're looking at about 6 hours of growth. And you will see that the ice has some texture to it. You will also see that there's a shimmer, which the starfish will be afraid of. Some shimmer in the water, and that shimmer is a consequence of brine. We can see that brine a little more clearly by putting some tracing paper in front of the tank and shining from behind to create what's called a shadow graph. And we can see that there are little narrow plumes of brine escaping from the sea ice into the ocean below. Just now we will look inside the sea ice to see where those plumes are coming from, but for now they exist, and they exist because of gravity. They exist because we started with salt water of a certain concentration. When we froze it, we extracted the water to form ice, and the liquid that's left behind therefore has more salt in it. It's enriched in salt. We have salty brine, which is denser than the original salt water, and because it's denser, it has the potential to drain outwards, heavy liquid over light liquid. And so the first thing we want to understand is this slide here. And if you really understand this slide, then I think you can say that you understand convection. Okay? So what's convection all about? Convection is about the release of potential energy into kinetic energy. Potential energy gets transported into kinetic energy of motion, of fluid motion. And our usual high school picture of that is of a ball on the top of a hill, which has potential energy, and if I push the ball off the top of the hill, it will fall down the hill, and it will gain kinetic energy as it falls. And now I want you to change your picture a little bit. Instead of a ball and a nice smooth hill, let's imagine that this is a snow-covered hill, and the ball is replaced by a toboggan with some noisy children on it. Okay? So first of all, the toboggan will go down, and of course they'll cause some plastic deformation of the snow, and we have to worry about the friction between the toboggan and the snow. Energy is going to be dissipated as we try to move. The children are very lively and very excited, and as the toboggan moves, they start falling off the toboggan. And so we lose mass, and eventually we lose our potential energy, okay, because of that diffusion of our mass to the surroundings. So we're trying to release some potential energy, and we're going to do that. Potential energy, remember, is mass times gravity times height. So the mass is the density, which depends on the salinity, times the coefficient beta. So we have a salinity difference between our starting position and our ending position, times a volume. So density times volume gives us a mass, times gravity, times the distance moved from our reference state. So this is potential energy, we recognize that. On the other hand, if we try to move through a frictional medium, a viscous fluid moving through past solid boundaries, we will dissipate some energy. And that dissipation is given by work done, and work is force times distance. Force is the pressure difference times the area, so that's force, times the distance moved, h minus z. So dissipation is just force times distance, the work done. We can estimate the pressure drop from Darcy's law through this porous medium as being the dynamic viscosity of the liquid times the velocity divided by the permeability, which has dimensions length squared, by the way, times so that gives us a pressure gradient, times the distance gives us the pressure drop, multiplied by the area gives us the force, multiplied by the distance. So the work done is there, the dissipation is there, and we're going to run out of buoyancy if we take too long. Okay? So if our time scale, which is the distance moved over our velocity scale, is bigger than is bigger than the diffusion time. So this is our sort of rate of loss, rate at which we're going to lose our buoyancy on that diffusion time scale. And we'll get an optimal conversion of potential energy into kinetic energy. So we only get kinetic energy if we've got some potential energy left over. We haven't dissipated it all. And we'll get optimal conversion actually if our time scale is about the diffusion scale and if the size of our parcel is comparable with the size of the vertical displacement. Another way to think about that is my dissipation, notice, is proportional to velocity. So maybe I'll get good conversion if I go slowly, then I won't dissipate so much. On the other hand, if I move slowly, then I'm going to lose all my buoyancy by diffusion. Okay? Now I can try and hold on to my buoyancy, not give myself enough time for it to diffuse away by moving rapidly. But if I move rapidly, I'll get lots of dissipation. Okay? So we have to find the sweet spot in the middle where I'm not losing my buoyancy by diffusion and I'm also not dissipating too much. And all of those considerations tell us that we'll get our optimal optimal conversion if something called the Rayleigh number, let me get a big stick, something called the Rayleigh number exceeds some value, some order 1 value, which we'll compute just now. And many of you will have studied Rayleigh-Bénard convection, for example, and have come across the Rayleigh number. This, I think, if you really sort of think about this, will give you a good understanding of what the Rayleigh number is about, good physical understanding. if you have met the Rayleigh number before, you may see that this is a rather strange Rayleigh number. It's the Rayleigh number for a mushy region, and it has some odd characteristics. First of all, it's a Rayleigh number that depends on the buoyancy given by the salinity contrast, and that's perhaps not a surprise. It says that the density change due to my differences in salinity are much bigger than the density differences due to the change in temperature. So the buoyancy is dominated by salt, so we want a solutal Rayleigh number. Usually with a solutal Rayleigh number, your dissipation would be determined by the rate of solute diffusion. But this Rayleigh number is not, although we're worried about buoyancy forces given by the salt field, it's the thermal diffusivity that matters, and that's because inside the mushy layer, the thermal field and the salt field are tightly coupled by the liquidus relationship. And I dissipate my buoyancy by dissipating heat. So I take a cold parcel and I try to release its potential energy by moving it downwards. But actually, when I dissipate the heat or sort of gain heat from the surroundings, what that does is to melt some of the ice, and that molten ice changes the salinity and dissipates my buoyancy. So my buoyancy is dissipated at the rate of thermal transport, even though the buoyancy itself is salt-driven. Okay, that's the most important slide of the talk. We're going to do some maths. This is my style, particularly because we're going to run up against lunch. I will go through the maths quite quickly, but it's there for your reference, and I hope it's laid out well enough that you'll be able to work through it if you want to. Okay? On this slide, I'm simply going to show you the equations that we use. I think this is the simplest set of equations that will describe the temperature, salinity, and solid fraction distribution inside a mushy layer. This is what I would call an ideal mushy layer. It's ideal in the sense that I'm ignoring the density difference between solid and liquid. Remember, that led to so-called brine expulsion, which we dismissed the other day. It ignores the diffusion of salt, which means we can't consider brine pocket migration, which we also dismissed the other day. And it's not written here, but when we apply boundary conditions, we will apply a boundary condition that takes the limit of the salt diffusivity being much, much less than the thermal diffusivity, which means we also won't have any interfacial segregation. Okay? So this is the simplest set of equations. Let's just remind ourselves of their structure. We have an advection diffusion equation for heat with an internal release of latent heat proportional to the rate at which the ice grows internally to the mushy layer. Okay? We have conservation of salt, so advection and diffusion that we're ignoring, and so we're just, the only way that the salinity can change is going to be by fluid flow. Okay? We have this tight constraint that we have the intimate contact between solid and liquid in the mushy layer, and so the temperature is going to be given by the local freezing temperature, given the salinity of the interstitial fluid. We're concerned about how fluid moves in the system. We need to describe that. We need a flow law, and we'll take the simplest possible flow law for flow in a porous medium, which is Darcy's equation that relates the velocity field linearly to the pressure gradient and the buoyancy force. Everywhere in the mushy layer. So they're decoupled in the liquid region. In the liquid, these equations are strongly coupled, and it's very important. No, 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 no. So one way to think about this, and we'll see it with some complicated, perhaps a little messy slide on the next slide. But one way to think of these two equations is this equation is an evolution equation for the temperature field or the salt field, because they're the same thing. And then this equation is an equation for the solid fraction. Okay, so that's, we have three, well, in principle, we have three dependent variables, temperature, concentration, and solid fraction. We have this tight constraint, which means we end up with just two dependent variables, temperature or concentration, one variable, and solid fraction, the second variable. So we also have a velocity field. So that's a final one. The usual solenoidal constraint and compressibility constraint on the velocity field, again, because we're taking solid and liquid to have equal densities. And we need a constitutive relationship, simplest one here, where I've written that the density is just a function of the concentration. Okay? So, one can take these equations, you can put them on a big computer and solve them. We're not going to do that. Okay? Now, I've got about 3 or 4 slides which will take you through an analytic determination of the conditions under which convection will occur in this mushy region. As I said, I will go through those fairly quickly. I hope there's enough detail on them that you can review them later if you're interested. Okay? But what we're going to do is we're going to step away a little bit from sea ice and go to actually this, more like this system, where the solid fraction is relatively low. Solid fraction in sea ice is quite high, actually. It starts at around 50 to 60% and gets up to 95%. In this system, we're at about 5% solid. May not look like it, but we're at about that level. And it turns out you can make a really nice simplification of these equations that allows you to make analytic progress and to generate some physical understanding and intuition. Okay? So that's what this slide is about. We're going to move into we're going to go into Sylvain's special apparatus, where everything is moving at constant speed v. We scale lengths with a diffusion length and time with a diffusion time. Pressure is at an obvious scale. We write a single dimensionless variable, which either represents temperature or concentration. They're the same thing in this system. And having done that, we identify 3 dimensionless parameters that govern this system. We have the Stefan number that we've seen before, the ratio of latent heat to sensible heat. We find an equivalent ratio for the concentration fields, just a concentration ratio. I tried very early on, when I started working on this subject, to coin the term compositional Stefan number, but it didn't stick. There are lots of very nice mathematical analogies between what's happening with the salt field and what's happening with the temperature field, where C really plays the same role for concentration as the Stefan number plays for heat. But we'll forget that for a minute. And then we have this Rayleigh number, which we understood a few slides back, but it comes out of the scaling that we've introduced here. And notice again that we've got buoyancy due to salt, dissipation due to heat. We've, as it were, thrown away any diffusion related to salt. And then, so that's, we haven't done anything yet, except make our equations dimensionless and identified some key parameters. But then we can take this very nice limit where we think about large Stefan number, and we've done that before. That gets us quasi-stationary in certain circumstances. We're also going to take large compositional ratio, and then we're going to do something that mathematicians like to do, which is to take what's called a distinguished limit. So although these two terms are both large, we'll consider that their ratio remains as an order 1 parameter. And if you do that, you get this reduced set of equations, which are simpler, and they're reduced in a very important respect, and that is that these two equations, the heat equation and Darcy's equation, now no longer depend on the solid fraction. So we can solve these as a purely thermal problem to determine the temperature field, or salt field, theta. Once we know the salt field, we can determine the solid fraction. So we've decoupled the problem. And we assume the permeability does not depend on phi, and one can do that with a Taylor expansion because our phi is of order 1 over curly c, which is very small, and so we take an approximation for that. It's not going to vary because of this limit. Okay. Good. So once we've got that, actually, we almost don't have to do any work because this is a solved problem. People have studied, essentially what we're saying is that the fluid flow, the convection, is the same as the convection in a passive porous medium, a porous medium of glass beads, for example. And that's a solved problem. This is the bit that's going to go quickly. So here are the two equations decoupled from the solid fraction field. We're hot at the bottom, cold at the top, which means that we are salty at the top and fresh at the bottom. So this is a system heated from below, but we're going to drive compositional convection because where it's colder is where the interstitial fluid is saltier. So remember, we're driven by salt. Convection, there's a linear temperature slash composition profile in the basic state, which we perturb sinusoidally and look for growth rate sigma. You substitute, you linearize, you worry about boundary conditions. Just like Lord Rayleigh, when he first did Rayleigh-Bénard convection, used the simplest possible boundary conditions that gave him an analytic answer. Here we're choosing boundary conditions that give you an analytic answer, so you can work through this, and that's to have no flow through the top of my sea ice and apply a constant temperature there, but where the sea ice connects with the ocean, we're going to apply constant pressure and a constant heat flux. And in that case, you can solve these equations very simply with half a sinusoid and find the eigenvalue relationship for the Rayleigh number, which comes out like that, for different structures in the vertical, sinusoidal structures given by n, and the most unstable mode has n is 0, so that gives us that relationship. And this is just the same thing again. Here is that relationship plotted against wave number, and this is a very classical sort of picture for convection, where we have the critical Rayleigh number as a function of wave number, which has a minimum at some critical Rayleigh number, and it says that if the Rayleigh number is below this value, then all wavelengths are stable, system is completely stable. If you're above this value, then there is a range of wave numbers that can become unstable, and you will see convection with that characteristic size. Okay. So we have instability if this omega Rm is greater than the classical result, which for this system is pi squared, and everyone knows that pi squared equals 10, and so things will become unstable if this augmented by omega Rayleigh number is bigger than 10. So this omega, let me write it up here. This omega is large if the Stefan number is large. And one way to think about that, so what this says is systems with large Stefan number will be more unstable. Okay? So why is that? If I yes, that was well, that was that was our mathematical trick. So we're taking a limit in which the Stefan number is large, the concentration ratio is large, but their ratio I'm keeping as order 1. Okay, it's a special thing. I mean, most experiments will not sit in this regime, but it's a nice regime where we can sort of solve everything analytically, and we can understand some key relationships, like the fact that we're more prone to convection at large Stefan number. Okay? So why should that be? Actually, let's think of it the other way around. We're less prone to convection if we have small Stefan number. And that's because at small Stefan number, I can melt really easily or dissolve really easily. Okay? And remember, it's that dissolution, that interior dissolution, that dissipates buoyancy. Okay? And so at low Stefan number, I will dissipate my buoyancy more easily, and I'm less prone to convection. Okay? So we can sort of understand some physics out of a reduced mathematical model. It's sort of useful for that sort of understanding. But I want you to keep this result in mind as we go forwards. Okay? And I've taken you through this very fast because I don't, you know, my goal isn't to teach you mathematics. It's to try to understand some physics and to understand some sea ice. But things are going to go unstable if this augmented Rayleigh number exceeds a value of order 10. That's the take-home message. Okay? Okay, you can relax a little bit. We're going to slow down. I'm going to try and slow down. And we're going to leave maths behind for a bit. So can we test any of this in the laboratory? So the first thing I want to introduce you to is a version of Sylvain's very nice apparatus. But ours is bigger. Okay. So it's also vertical rather than horizontal. So here it is here, but it's the same principle. We have two heat exchangers. One's kept warm, the other's kept cold. We have a cell that can translate past the heat exchangers. Our cell here is about 40 centimeters tall, but the active region 10 centimeters across. In these experiments I'm going to show you 6 centimeters between the heat exchangers, and the gap between the glass plates that are front and back of the cell is about 3 millimeters. We're going to fill this with salt solution and start to freeze it. Okay. So before I start the movie, let's just get our eye in a little bit. I'm going to be concerned about the Rayleigh number. And the Rayleigh number is large when length scales are large. The Rayleigh number is large if I have a deep mushy layer. And in this directional solidification system, I get a deep mushy layer if the velocity is small. Okay, the thickness of the mushy layer, by the way, sorry, let me just get your eye in. This is salt solution. The light blue here is mushy layer, and then this is about minus 21 degrees Celsius. This is colder than minus 21. So in this region, we have the ice is frozen and the salt is crystallized. This is completely solid. So we have completely solid, mushy region, liquid region. Okay? The Rayleigh number depends on the thickness of this region. And that thickness depends on the speed. As the video progresses, we're going to go from a high speed of 2 microns per second to a low speed of 0.5 micron per second. So look out for that change in speed, and we should see the thickness of the Rayleigh number increase when we change speeds. And we've arranged that that increase in thickness will give us an increase in Rayleigh number, taking us beyond the critical Rayleigh number for convection. So it is moving. Have a look here. But we're sitting in the moving frame of reference. So really this is growing downwards, except we're tracking that front. I think the change of speed just happened. And we're starting to see some brine plumes. Those brine plumes are coming out of imperfections in the mushy layer. And then we speed up again. When we speed up again, the convection stops and everything heals up. Okay. So this is just a nice sort of visual characterization of the importance of the Rayleigh number in determining whether or not there is convection. And that Rayleigh number will also determine the harder question, which we haven't talked about yet, is actually how strong is that convection once we've exceeded the critical value? What is the brine flux from the mushy layer into the liquid? Okay, well, it's nice to look inside. So far, I showed you a shadow graph where the mushy layer was just black. Here, well, it's light blue, but it's no better in the sense that we can't see inside. So let's have a look inside the mushy layer, which we can do using MRI. This is a horizontal cross-section, just a single picture. Here is a poor man's video, I think about 6 frames, because these take a long time to acquire, these pictures. And we saw the evolution of the ice going downwards and the development of a dissolution channel, a brine channel. And what's happening here is that we're above the critical Rayleigh number, so there's convection. Convection causes a cellular motion up here and down here. Where I have motion from cold to warm, that's a motion that carries relatively fresh liquid to relatively salty region. That fresh liquid, relatively fresh liquid, can redissolve the ice either side of it, like throwing salt on the roads. So whenever we have flow from cold to warm inside a mushy layer, we will get dissolution. And we can create a channel, a dissolution channel. And the primary route for salt out of the mushy layer into the ocean is via these brine channels. So there's a slow sort of permeation of the brine through the mushy layer, eventually into a brine channel, and then out as a plume that you saw at the beginning. We can use a coarse resolution on our MRI to take an average, really essentially horizontal averages of the solid fraction, or porosity actually is what is measured directly, as it evolves in time. I haven't shown the theoretical curve, but this red set of dots, which were taken in this window between 1.5 and 3 hours, actually sits right on top of the theoretical calculation that we made in my last lecture. So that is the solution. That is what you have when there's no convection. Okay? But here we've scaled depth with the actual thickness of the mushy layer. When the mushy layer was thin at early times, there was no convection. When the mushy layer got thicker, convection could begin, and convection takes salt through the mushy layer and down through the brine channel out into the ocean, which means this region here has a bulk salinity that is getting less and less. Okay, we're taking salt out of this region. And as we take salt out of the region, the solid fraction of ice increases. Okay? Another way of thinking about it is we take this very salty brine out through the brine channel into the ocean. It needs to be replaced just because of continuity of mass. It's replaced by relatively fresh water from the ocean coming into the mushy layer, And because it's relatively fresh, some of that water will freeze and increase how much ice there is and reduce the permeability. And that reduction, if you look spatially, the region over which the porosity is decreased corresponds to the region in which there are dissolution channels, brine channels. Okay, that's all very nice. In the laboratory, we can measure some of these things. Is this what we see in nature? So I was very fortunate to go with some colleagues in 2001 to Svalbard. This is us, well, not me, because I'm behind the camera, but my colleagues with their snowmobiles in the middle of a fjord, okay? So if it weren't winter, we'd sink, but these are driving on the frozen seawater. And the first thing we did, which took us 3 days hard labor, was to cut a 3 meter by 3 meter hole in the ice. And the ice was 60 centimeters thick at this stage. We did it with hand saws. We didn't have any dynamite or electric drills or anything like that. So we cut by, and you can see the blocks of ice that we cut out and pulled out manually out of that hole. And then we deployed our instruments into the hole. There's a thermistor chain here, and there's, I'll show another schematic in just a moment. This is our little conductivity probe that I mentioned the other day to measure solid fraction. So this was very much a preliminary trial of all of this. We didn't get any useful data, but fortunately in life there are things called PhD students. And so this is my PhD student, Dirk Notz, who then went out to the field for the following 3 years, and on the 3rd year got a really nice set of data. The first 2 years was all about instrument development and etc. So this is Dirk's data from his PhD, Dirk Notz. Here's a schematic of our instrument again. It's just a conductivity probe measuring AC impedance, which gives us, essentially, as I said the other day, all the electrical charges are really being transported by ions in the brine, and so the conductance that we infer is directly proportional to the porosity, to the brine fraction, and so we get a measure here. And I just picked out one of the profiles in red, so you don't, you know, there are lots of lines to look at. Let's just look at one of them. So here is a profile of porosity, or solid fraction. It's been inverted for the solid fraction, which you see is very close to 1. I was saying sea ice has ice fractions very close to 1 for about half the depth. And then there's a region where it tends relatively smoothly to 0, okay, at the edge, at the ocean, the mush ocean boundary. And once we have the solid fraction and we measure the temperature field with a thermistor chain, we can determine the interstitial concentration, that's this, and multiply by the porosity to give us the bulk salinity. And the bulk salinity, well, here's the bulk salinity of seawater, about 33 parts per thousand. But in the top part of our ice, at least, that's reduced to just a few parts per thousand. But again, there is a variation through here, which is where all the action is taking place. Everything is happening in this lower portion of the sea ice, and we get this variation in bulk salinity from the region where we've had lots of brine drainage to the ocean values here. Okay. So once we have these two quantities, we can compute the local Rayleigh number. Okay. So here it is. We can determine it from our data. And now remember that the Rayleigh number depends on thickness. Let's imagine for a moment that no convection happened. We just take our diffusive solution, and the mushy layer, you know, grows like square root of time, roughly. The mushy layer gets thicker and thicker and thicker, the Rayleigh number therefore should get bigger and bigger and bigger. And if you didn't allow any convection, by 86 hours, the Rayleigh number would be a few hundred. Okay. So what's happened? Once the Rayleigh number exceeded its critical value is about 10. Once it's exceeded a value of about 10, you start to get some convection. What does the convection do? It takes brine out of the mushy layer. It brings relatively fresh ocean water into the mushy layer, where it freezes. And as it freezes, it reduces the porosity and reduces the permeability. So H is increasing with time. The permeability is decreasing in time. And these things compensate each other. There's a self-regulating system so that the Rayleigh number, peak Rayleigh number, stays of order 10, roughly constant. And that's going to be an important modeling consideration. Okay. So what can one do theoretically? I'll just, in sort of one slide, show you what we have done without taking you through any of the details. First of all, I'll show you another experiment. This is a, pictures tell lies. This is an experiment that was actually performed the other way up. But mathematicians can stand on their heads very easily. You just multiply gravity by -1. Okay? So, and we put ourselves on the other side of the phase diagram. So it's not ice, it's ammonium chloride, but it's the same principle. So we formed a mushy layer, and those with good eyesight will see that there are lots of little dendrites in here, but we're not concerned with trying to model the shape of the dendrites. We basically want the envelope, which gives us the thickness of the mushy layer. We'd like to know something about the flow through here, and that flow, which is broadly up from the ocean into the sea ice and down through a dissolution channel or brine channel, causes this dissolution channel. We'd like to be able to predict the size of that brine channel, and we'd like to predict the flux coming out of it, the flux of brine coming out of it. This was an experiment that I first saw in a seminar at my department in about 1980. And it fascinated me. And I sort of worked on solidification for a long time. And we eventually answered the question, how is this width determined, in a paper that was published in 2004. So just message to PhD students, sometimes you're fascinated by problems that can take a couple of decades to get to the bottom of. What's the challenge? The challenge is not in the differential equations. Differential equations have essentially been known since the 1960s. They were mostly used diagnostically by metallurgists who can't see into their systems, but they can measure temperature. Can you, by measuring temperature, infer something about the solid fraction? Well, yes, you can by using these phase relationships and using those equations. People didn't try to solve those equations to make forward predictions until about the 1980s. And as I say, we couldn't solve this problem until about the turn of the century. And the problem is that all the difficulties in mathematics, applied mathematics, come in the boundary conditions. And it was determining the physical boundary conditions. So there are two boundaries here. One here is here between liquid and mush. And we had the marginal equilibrium condition I mentioned the other day was something that I postulated shortly after my PhD and worked very nicely in non-convecting systems. Okay? So this boundary condition we've known for a long time, and it works well. It turns out that it works provided that the material transport is from the liquid region, the bulk liquid region, to the mushy region. Here we have another boundary between mush and liquid, but in this case the material transport is from the mushy region to the liquid region. And that turns out to be harder to think about, but we did finally come up with a boundary condition that applied there. And then my next picture is going to be a hybrid calculation where, you know, I'm not a great numericist. So, and actually even the numerics we did do, when I say we, I don't include myself. The numerics I show you was done by a postdoc, but I did contribute to the modeling of it. And we tried to simplify things. So there's a lot going on in this picture at different scales. And mathematically, you can exploit long, thin scales by using something called lubrication theory. And so we solved what was happening in this channel analytically. We also solved what was happening in a plume, an idealized plume, analytically. And we used those analytic solutions to provide boundary conditions to a numerical calculation in the mushy region. And this is the consequence of that. Okay? So this is a free boundary that has to be determined. This green line looks like a line, but actually analytically we know how to turn that into a channel width and shape. And the numerics then determine the temperature field in red, the solid fraction field in green, and the streamlines in blue. So all of that is calculated. One of the things you notice as you come towards this brine channel is that the solid fraction first increases before it decreases to 0 at the channel wall. Okay, so there's a sort of halo of high solid fraction around this chimney. And that's actually something I could have pointed out earlier. It's something we see in the MRI signals as well. So this is real, and it's captured by this analysis. Okay, so that's great. This is expensive. The scales for this is a few centimeters. In the field, it would be a few tens of centimeters. This channel width is a few millimeters. And this is, well, at the time, a few hours of computation to do all of this. And we'd like to put this into a GCM that has one grid point every 30 kilometers and maybe, 4 to 6 grid points in the vertical. So that's the challenge. And that came down to another very good PhD student, David Rees-Jones. And what he did was to look, we already had analytic solutions for what was happening in this brine channel, which in metallurgical context is also called a chimney. And David was able to use some boundary layer analysis to compute this region of enhanced solid fraction around the chimney. And it had been argued for a long time which was the dog, which is the tail. In other words, where is the real driving force for convection? And the assumption had been that the engine of this system was what was happening in the brine channel. Turns out that the brine channel is just the tail of the dog, and the real engine is this active region around the chimney. And the chimney is a sort of rather passive manifestation of the downflow causing dissolution. Okay? But now we can essentially solve this region analytically using boundary layer theory, and then most of the flow is just a classical corner flow, which again you can calculate analytically. And what's important about it is that the vertical velocity of this corner flow, the vertical component, is uniform. And that's great. Because if I have a uniform vertical velocity over most of the mushy layer, I can use that uniform flow in a one-dimensional heat equation. So I really just have a one-dimensional heat equation through this region with a flow strength that's determined analytically in this region. So that's great news. So this was the end of the story, which is great that you can put all of this together into a one-dimensional sea ice model, which includes the strength of convection through this vertical velocity, mean vertical velocity in this outer region, which is determined completely analytically provided you know the depth of this convecting region. Sorry, the colors are not great. That should be like pale blue and then white. I don't know if you can just about make that out. What you find is that there is an active region that's convecting, and there's a passive, stagnant region which did convect in the past, but is no longer participating in convection because the Rayleigh number is too small. The permeability has got too low for a parcel of brine from here to escape into the ocean. And I'll just make the point that this says nothing about the formation of brine pockets. Convection doesn't stop because the brine has been encapsulated in ice. It stops because the Rayleigh number has fallen below critical. There's still about 5% water. Okay. Now there's a question. I mean, there are people there who say, 5% water, all the brine is in pockets, and therefore it's immobile and won't move. That may be true, may not be true. It's not important. What's important is that the Rayleigh number has fallen below critical. Okay. So I don't think this stagnant region is necessarily a consequence of trapping brine into pockets. And I just thought I'd finish with some calculations, sort of thing that can be done. Notice that all of this complication doesn't change the general picture that the zero-layer Sentner model does a pretty good job, a linear temperature profile through the mushy layer. But we can determine the evolution of the solid fraction, the bulk salinity, which is the thing we measure in the field, and the local Rayleigh number. That's at very early times. But if I run it longer, we start to see this general desalination, okay? And the convection sort of stops above this region. Again, I don't know what you can see from that distance. There should be a light blue region up to about here, which has active convection, and then this region here is stagnant, where the Rayleigh number has exceeded this critical value, and we get the variation in bulk salinity, as we saw from the field measurements, from the ocean value into the interior value. The nice thing about this is that it's dynamic, and so it responds to changes in weather. So if I get a warm spell coming through, actually, if I warm this ice, then I open up the pores a little bit, and I can get another flushing event. I can reinitiate the convection. We'll start again and get rid of a little bit more salt. So this is very responsive to changes in weather. So capabilities and characteristics. We determine this buoyancy flux dynamically. We still have a parameter in this system. The parameter is the Rayleigh number. But actually, that's something that's computed as we go. Really, the parameter in the system is the critical Rayleigh number. But that's a number that we know is about 10. May not be precisely 10, but we've got some leeway to adjust it within our climate model, but not a lot. But we're not ourselves forcing the value of solid fraction or of bulk salinity, which was the previous state of affairs. In experiments that I haven't shown you, when the layer is just starts growing, there's a period, one where you did see it actually from the MRI. There was a period of about 3 hours before there was any change in salinity, okay? And you can do that by measuring the salinity of the ocean underneath as well, and you find that initially there's no brine flux, and then you get a sort of critical thickness where you start to get a brine flux, and so we can capture that delay in the onset of convection. And this is the point I made just now about reinitiation. And this is an important point. It was something that was known as the Baltic Sea problem for a long time. The Baltic Sea is relatively fresh in its surface layers, and the climate models before this sort of modeling predicted that salt was sucked up from the ocean into the sea ice in the Baltic regions. And that's because it assumed that the sea ice has a certain fixed salinity, okay, which was greater than the salinity of the Baltic Ocean. So, you know, you can take fresh water and freeze it and form salty sea ice. You can't. So finally, what have we seen today? Convection begins at critical value of the Rayleigh number, order 10. That we can really have a dynamic parameterization of convection at a scale that's useful for climate models, parameterized in terms of a Rayleigh number. And we've seen that that Rayleigh number, very sort of special sort of Rayleigh number, depends on permeability and solutal buoyancy, but thermal diffusivity, because of the way that the temperature field interacts with the salt field. Okay. Maybe I'll leave things there. Thank you very much. It's been fun.